All right, so we are looking at a new type of compound here, covalent compounds as opposed to ionic compounds. And we're going to look at this word covalent specifically. We got a prefix on here. So co, think about, something like community. And in a community, you got to share resources. And then we have this term valent, which looks an awful lot like valence electrons. And really that's what's going on here in a covalent bond. Covalent compounds are situations where valence electrons are shared in their bonds, where in the previous case, ionic compounds have that give and take. So one element is going to give your cation and take those electrons. The anions take them in their bonds. So different situations, still a way to get elements to bond to each other. So types of elements, we've talked about these before. In ionic compounds, you have your cations, which are typically going to be a metal element, and your anions, which are typically going to be your nonmetal. So you got both. You got your positive charge, your negative charge, and these things stick together. In covalent compounds, there's no charges involved. We're sharing the electrons, nothing's permanently positive or negative. We're only going to be dealing with nonmetals only. So things like carbon and hydrogen and oxygen and, fluorine, nitrogen, etc. Right side of the table. So let's look at some structures here. We can change the page. Go to, here we go. So here we are looking at sodium chloride. We have a model of it here. You can see our little sodium ions, little chloride ions, and they're repeating themselves in this structure. You've got a negative charge, our chloride, bonded to a positive sodium, bonded to a negative chloride, which is bonded to a positive sodium, so on and so forth. You have this nice, consistent, repeating structure, and that produces, on our scale, or at least a little bit larger, the very same kind of shape. The red and the green looks like a cube. It forms this cubic shape. Well, individual salt crystals are going to retain that shape due to the way that ionic bonds form. So we can look at that and address that here. So when we look at ionic compounds, they are going to have these repeating patterns of your cations and anions. And they're going to form this large, and large in the sense of number of ions involved, crystal structure. Draw a little diagram just to help remember that. We got a positive bonded to a negative, bonded to a positive, and so on and so forth. And everything interlocks there nicely due to those charges. Covalent molecules, and that's what we are talking about here. These are really molecules. When we hear that term, we're talking about individual covalent compounds. We can look at a little video here. And we have some covalent molecules going around. We have water. You can see little positive and negative charges. These aren't full positives and negatives, but if you remember anything from biology, water is polar. And you can see it's moving around, sticking together. But it's not in that big uniform structure. These are individual molecules floating around. So when we talk about the structure of a covalent compound of a molecule, we're really referring to one individual structure of those atoms that are bonded together. And obviously, you have a glass of water or something, you're going to have a lot of these in the same space interacting with each other, but that doesn't mean that they are all actually locked into the same structure like it would be for an ionic compound. So, last bit that we want to talk about is properties here. So bump that back. So common properties, first of all, for ionic compounds, think about table salt. They are generally solids at room temperature. Baking soda, sodium bicarbonate, same deal. It's a solid at room temperature. And as a result, they generally have higher melting boiling points. You got to break apart all of those attractions locked into that structure. So higher melting and boiling points. We can look at this little video simulation thing again. We've got table salt here, and we put in our sodium chloride into water, and it breaks apart pretty quickly. You get those oxygens attracted to the sodium, you get those hydrogens attracted to the chloride, and this isn't true all the time, but a lot of ionic compounds are soluble in water. They can dissolve, and when they do dissolve, we can go to another screen here, and I already kind of gave it away. Let's reset that. Water on its own isn't the thing that actually conducts electricity. When I tell you to get out of the pool, when there's a thunderstorm, it's not because of the water, but because of those things that are dissolved in it. So when we have ionic compounds like salt dissolved in there, we just saw it, you get those little ions, those charged particles floating around. They can conduct electricity. This is how we can tell if ions are present. So they can conduct when they're dissolved. All right, so let's finish this up. What's nice about our covalent compounds is they're, for the most part, not exactly the opposite, but they are definitely different than the ionic compounds. You can get all different states of matter at room temperature. So quick example of this, think about water. At room temperature is a liquid. Carbon dioxide is a gas, and something maybe like wax or sugar, it really depends on their structure, which we're going to dig more into, but overall we have generally lower melting and boiling points. They're not held together as strongly. And same thing depending on the structure. You end up with stuff that's sometimes soluble in water. So something like sugar. Sugar is a good example. We can even see it here. If I reset this, we have some sugar molecules present, and I can drop these in here. And you can see, the water can attract to it. It can separate those out. It doesn't break them into the individual ions or atoms like it did for the ionic compounds, but it still is possibly soluble. There are other compounds. Think about like oils. Oil and water do not mix. Oil is a covalent compound. It really depends on the structure. And we can look at this too. So we've got a little sugar container. can dump that in there. That looks like plenty. And we can check our conductivity. And we got nothing. Because when you look at this, looking at sucrose, which is sugar, it doesn't form charged particles, just individual molecules floating around there. So it's possible that our covalent compounds dissolve, but when they do, if and when they do not conduct electricity. So there we go. Some basic definitions, properties of ionic and covalent